Good morning. How is everyone today? Good? All right, I hope you're all awake and you have recovered from your jet lags from various corners of the world. I am very happy to be here today. This is my first time to Portugal and to Lisbon. Today, I would like to take a look into the future and let's see if I can get all of this to work. Yes. And try to predict what challenges and opportunities lie ahead for us in terms of wireless and radio design. I will begin with some introductory remarks and predict some applications and trends in wireless and radio design. And then I'll focus on the problem of mobile terminals, which will be the major bottleneck in communication in the future. Then I'll focus on receiver design and transmitter design for mobile terminals. And if we have time, talk a little about the problem of phase noise, and then summarize with a conclusion. Since we have many professors and students in this audience, I thought I'd start with a quiz. Of the devices that I will show you, which one has not used wireless technology? The light bulb, the toothbrush, the pacifier, or the shoes? And the answer is they all have. So it's interesting, in the case of pacifier in particular, why should you put wireless technology in a pacifier? Well, and I'm not making these up. This is all based on published information. Well, if we can have sensors to measure the movement, we can tell when the child is asleep. Moreover, if we can measure the saliva and its constitution, we can even determine if the child is sick. So there are many interesting things that we can do with a simple pacifier. All right, well, let's start with our typical user who has some sort of mobile phone and place on him a bunch of sensors to measure his blood pressure and sugar level and physical activity and mental activity and everything else, and submit them and transmit them wirelessly to his doctor's office so that he can be monitored for health reasons. Then let's give him a house, and in this house we have some typical appliances that are wirelessly connected to the internet, and when the load on the power grid is heavy, we can request these devices to lower their load on the grid. Let's give the children some wireless toys that they can play with, and then when they go to sleep, let's monitor their bed and the movement to make sure that they sleep well and they don't have any restless nights. And then on top of that, let's deliver our goods using drones, and then let's give this guy a self-driving car, and along with that, some intelligent smart highways that can monitor the movement of vehicles and coordinate driving among the vehicles so that the driver can relax and maybe read his newspaper or his iPhone. And finally, for everyone to communicate everywhere, let's place 6,000 microsatellites around the Earth to cover the entire planet with wireless communication. And again, I'm not making any of this up. This is all based on published information. All right, so this predicts that there will be many applications for wireless in the future. The toy market itself is $80 billion worldwide. And if we can penetrate only a few % of that, that's still a significant amount of revenue. But more importantly, there are automotive applications for smart vehicles on highways, wearable electronics, wireless health, smart home, smart metering and utilities, and finally, eventually, smart cities. I would like to focus on a few of these just to see what lies ahead for us in the future. Wearable electronics has become somewhat popular today with, for example, the Apple Watch and these health devices that we can wear to track our vital signs. But eventually we will have also devices embedded in our clothing to monitor our health. And presently, according to Cisco, these devices amount to about 170 million worldwide. But it is predicted that by the year 2019, they will grow by about a factor of 4. For wearable electronics, the main issues are cost, power dissipation, and form factor. The next application has to do with medicine and healthcare. Today, of the 7 billion people on this planet, about 4 billion don't have adequate healthcare. And I would like to quantify that as follows. If we look at the density of physicians for every 10,000 people, in Europe we have 33 physicians. In Africa we have 2.6, and the world average is about 14. The number 14 might be misleading because if you look at some countries, they are frighteningly low in this respect. For example, African countries are about 0.1 to 0.2 physicians for every 10,000 people. This amounts to about 10 million physicians today worldwide. And if we want to double that, we have to train 10 million physicians, and that won't happen even in 1 decade. It will take several decades. So what are we going to do in the meantime? Similarly, we can look at the hospital bed density around the world. And we see that, again, for every 10,000 people, Europe has about 53 beds, whereas Eastern Mediterranean countries have about 8. And again, some extreme cases are quite scary. You see that around 1 or 2 beds for every 10,000 people. So these indicate that if we want to look at the healthcare worldwide, we probably have to go to a distributed healthcare system, as they say, a physician in every phone. And the idea would be that we have the sensors installed on people, especially people who need medical care, and we monitor their vital signs and wirelessly transmit them through internet to the physician's office. And then the physician can at least monitor these and determine at what point the patient needs care or a doctor's visit. For this, of course, we can build various devices. There are numerous examples in the literature where we have some electronics, some wearable materials, and then some energy harvesters to power up the devices. And what's interesting is that it's not just a matter of sensing for vital signs, but eventually it's also a matter of actuation. So it is conceivable that eventually we can administer injections or electric stimulation of the brain and many other things remotely. We don't need a doctor present. So with all of these things connected to internet, it is expected that by the year 2020, there will be 33 billion devices connected to Internet of Things. And that means that pretty much any device around us is monitoring our movements and reporting our movements to some central place. So that's a little scary in terms of privacy. We won't have much privacy, but that's okay. What's also interesting is that if we have 33 billion devices and they need little batteries, apparently the total lithium that we have on Earth will not suffice to build 33 billion batteries. So that underscores the importance of energy harvesting for these devices because we just simply do not have enough batteries to put in them. So it's not just a matter of design for low power consumption, also low voltage design, and finally being able to design an efficient energy harvester on the device. So for Internet of Things, we have some critical parameters, cost, power dissipation, supply voltage. We need energy harvesting, and the form factor has to be small. Less important are, for example, noise figure, linearity, channel bandwidth, meaning data rate, because these are usually slow links. And then the transmitter output power and phase noise also can be relaxed. In order to reduce the power dissipation, one can employ many different techniques. One is to try to merge different stages in a typical transceiver, and the other is to eliminate stages that may not be absolutely necessary. So I'll give you some examples of these. For example, for Bluetooth low energy, which is a relatively relaxed standard, rather than have everything, a low noise amplifier, quadrature down conversion mixers, and local oscillator, and amplifiers and filters, all as successive stages with their own bias currents, etc. One can envision a situation where we begin to merge these functions and try to reuse the supply current for a number of circuits. And one good example is from University of Toronto. In this paper published this year at ISCAS, they merged the low noise amplifier, the mixers, and the oscillators, and the quadrature separation, and even the filtering in the baseband, all so that they can draw one bias current for all of these circuits. And this results in a participation of 600 microwatts with a supply of 0.8 volts. The noise figure is okay for Bluetooth low energy, 15 dB, and the IP3 is minus 16 dBm. Another possibility is to try to eliminate stages. So again, if you look at our front end, we can ask what the role of this LNA is. We know that it has to provide voltage gain and input matching. Fundamentally, that's all that is necessary. So maybe instead of an active stage, we can use a transformer to provide both of these functions. And the transformer can provide some voltage gain, maybe by a factor of 4 or something, even though nominally this is a 1-to-6 transformer. And then it can also help in impedance matching if we follow it by some passive mixers. And this overall front end can give us a zero power front end with a noise figure of 4.5 dB and a voltage gain of 12 dB. Now, of course, we have to add more bells and whistles. We have to add some filters and an LO drive and so forth. And these will bring us to a power dissipation of 11.6 milliwatts with a noise figure of 5.4 dB and a sensitivity that is better than what's necessary for Wi-Fi applications. All right. As you have seen, the mobile device plays a central role in everything that we will be doing. And as such, it becomes a bottleneck in the communication. This can also be seen by predictions by Cisco. We see that the traffic that goes through mobile devices worldwide today is around 5 exabytes per month, and it will go up by about a factor of 5 by the year 2019. 1 exabyte is 10 to the 18 bytes. That's about 200 million DVDs if you want to visualize it. And this tells us that the mobile device plays an increasingly more critical role in our communication. Now, does it mean that we talk so much? Do we talk worth 5 exabytes per month into our cell phones? No, actually, what's happening is that it's the video that's taking up all of this data. So the data today is about 60% out of from video, mobile video, and then by the year 2019, it will be more than 60–70%. So we are more inclined to watch videos than to read text or to send text. So this is the trend that we face. Now, of course, when we have mobile video, we would like to have a higher data rate for our phones so that we can watch a reasonable quality video. But unfortunately, as you can see, the data rate that we have in cellular systems is not going up that much. Even in 4G, the data rate will be about 14 megabits per second. So the way this will be handled, according to Cisco, is with offloading to Wi-Fi systems. So Cisco says that by the year 2019, about 54% of that traffic will flow through Wi-Fi rather than through cellular systems. And that places greater emphasis on Wi-Fi design in terms of power consumption, cost, performance, and form factor for future mobile terminals. So we see that we have two somewhat separate considerations here. One is a cellular system that has to sustain a greater load as we go along, and the other is a Wi-Fi system and its variants, including 11AC and probably eventually the 60 gigahertz WiGig, that all have to take that offloading from the cellular system. All right, so if we summarize what's necessary from a mobile terminal today and in the future, these are all well known: low cost, low noise figure, high linearity, low power dissipation, high blocker tolerance, wide frequency range, low phase noise, and high transmit output power. Perhaps the most difficult part of a radio design is the transmitter output power. That has been the headache for us for decades, especially if linearity is a concern. So we have nice solutions for many other building blocks in the transceiver, but the power amp still defies an elegant solution. However, there are two trends that will help with the transmitter design. One is the migration towards picocells Because the cells will be smaller, the transmitter output power doesn't have to be as high. And the other is the Wi-Fi offloading, as I mentioned before. All right, so let's dig into this a little more and see where we stand today. Today, we have a mobile device that has to support up to 15 frequency bands. And because of these bands and because of the large interferers, as we call them, blockers, we do have to use external filters. So we have a whole bunch of soft filters, other filters outside the transceiver chip. And that gives us significant cost and form factor compared to the chip itself. So what we are hoping is to be able to omit all of these off-chip filters by circuit design. We'll have to see what it takes to get there. Also, eventually if we do that, then the cost will be determined by the chip itself, which means we would like to minimize the size of the chip. And as far as the analog and RF sections are concerned, we would like to, for example, remove inductors altogether from our transceiver chips. And that's somewhat possible. This is an older chip just to show you an example of the tens and tens of inductors that are used to get the circuit to work for 11ABG. But the trend is to remove inductors as much as possible. And then finally, we would like to support many bands with minimal overhead in terms of chip design. And also, in order to increase the data rate, we would like to support carrier aggregation, meaning using more than one channel for transmission and reception. All right, so how do we go about doing that? What type of radio architecture do we use? Well, back in 1995, Joe Mitola proposed the idea of a software radio. He said we just digitize the signal from the antenna, do everything in the digital domain in the receiver, and similarly for transmitter, we drive the antenna by a DAC, and before that, everything is done in the digital domain. So that sounds like a great idea. Unfortunately, we haven't really got there. The A to D required for this type of receiver is really tough to design, even with today's technology, even for simple systems such as Bluetooth. The closest example we can find are continuous time signal delta modulators. Here's an example from this paper where we take the signal from the LNA, apply it to a continuous time signal delta loop so that we digitize the signal and we downconvert the signal at the same time. And that allows us to shape the quantization noise out of the channel of interest and then obtain the channel at some lower frequency. Unfortunately, these efforts have not been competitive with other receiver designs. Here, as an example, we have 80 milliwatts of power and 16 dB of noise figure in the presence of a minus 18 dBm blocker. As you will see later, we can achieve better performance than this using more conventional non-software radio approaches. Well, so then after software radio came the concept of software-defined radio, where we said, okay, well, we'll go with a more conventional approach, but we'll have many flexibilities in the design in terms of programmability and software control of the corner frequencies, the gains, the bandwidths, and everything else. And after that came the notion of cognitive radios and eventually the universal radio. A universal radio is a radio that has everything. It works across a very wide frequency range. It just doesn't have a refrigerator in it, but it does everything else for you. All right, so how far are we from a universal receiver? So let's just try to write these down, the specs that we would expect and see. We would like to have a low cost, so that means preferably no inductors and no off-chip filters. Low noise figure, high linearity, low power dissipation, high blocker tolerance, and a wide frequency range. For example, from tens of megahertz to 10 gigahertz or maybe even higher. All right, well, I would like to attempt to approach these specs and see what we can do. So let's start with a simple low noise amplifier, something like a 3-stage amplifier with feedback. This allows us to achieve a few of these. We can achieve we can avoid inductors, we can have a low noise figure and low power dissipation and a wide frequency range. So that's good, just at least for the front end. Okay, then, but there are all these other issues, right? Off-chip filters, how do we take care of that, especially in the presence of large blockers, high linearity, and high blocker tolerance. So here's an example from GSM that tells us how serious the situation might be. We can see that in addition to the desired channel at -99 dBm with a 200 kHz bandwidth, we have at 20 MHz offset a blocker at 0 dBm. And this combination has to flow through the receiver and not saturate the receiver. An interesting development that has taken place in the past 5–10 years is the concept of end-path filters or translational circuits. Sometimes we call them commutated networks. And the idea is pretty simple. If we take a filter prototype, for example, an RC circuit, and replace the capacitor with a commutated network, a network that periodically switches to the output, then we translate the frequency response of the circuit to the harmonics of the LO. This was predicted by Smith back in 1953, this exact circuit. Smith also predicts that the bandwidth of this translated frequency response is approximately given by 1/pi times n, the number of capacitors, times the source impedance, times 1 unit capacitor. So that's a critical number to remember because we're trying to achieve a very narrow bandwidth for channel selection, and we want to minimize the total capacitance that we use on the chip. Also, what we see is that as we go away from the center of this translated transfer function, we reach a finite rejection because at this point, this network can be considered a short circuit and is limited by the resistance of these switches. So the rejection outside the channel is given by the ratio of the switch resistance and the source impedance. So that's also good to remember because eventually we need to work out these numbers. Okay, so can we apply this trick right at the antenna so that we remove blockers even before we enter the receiver? That would be great because then all the circuitry following the antenna would be relaxed in terms of linearity and noise and everything else. Well, so let's do that. Let's place some of these commutated capacitors at the antenna, knowing that we have a source impedance of 50 ohms. So with 50 ohm source impedance, we figure out how much capacitance we need to achieve 200 kHz of bandwidth from Smith's equation. And then from the out-of-band rejection, we also decide on some number, let's say 20 dB, and that gives us the necessary switch resistance. And these amount to this much, 28 nanofarads of capacitance and a 5 ohm switch resistance, neither of which is really practical for chip design. The linearity of the switches also becomes a concern when we impress upon them a 0 dBm blocker. Okay, well, let's take a different approach then. Remember this little integrator that we learned in basic electronics? And remember that this capacitor can be viewed as Miller multiplied at node X. So at node X, we see CF times 1 plus A0 to ground. Well, there's another approach. Why don't we place this circuit in a black box and find the Norton equivalent of the circuit in this box, which appears as shown on the right-hand side. We see that we have a current source, but what's interesting is that the resistance is multiplied by 1 plus A0 as is presented to the capacitor. So this is another way of thinking about Miller effect, right? Rather than say we have capacitor multiplication, we can say we have resistor multiplication. Now, this transformation holds even if the capacitor is replaced by a commutated network, because the circuitry in the black box is linear and time invariant, so I can simply replace it by its Norton equivalent. So the key point here is that the resistance presented to this capacitor array has gone up by 1 plus the gain of the amplifier. And if you remember Smith's rule, for a given channel bandwidth, this translates to proportionally smaller capacitors in the array and saves area. One other interesting thing that comes out is that if we draw out the resistance of these switches explicitly, as shown here, this resistance is also compared against a source impedance of 1 plus A0 times Rs. And again, the resistance of the switches can be higher proportionally because it is divided by 1 plus A0 times Rs. So both of these benefits allow us to build a relatively simple circuit, which we call a Miller bandpass filter. So I replace that LNA with this LNA I showed you before. I have the commutated capacitors out here, and I'm driving the circuit by an antenna. And I have limited the total capacitance to 2 nanofarads. And what we see is that indeed we can achieve a bandwidth of about 200, 300 kilohertz with a pretty good noise figure for this receiver front end. And we have channel selection, and we have also down conversion because we can take the signals anywhere out here as the baseband signal. So this brings us to this checklist again, and we see that we have satisfied some of these requirements, but we have to think about linearity and blocker tolerance. Can this circuit tolerate a 0 dBm blocker? So no problem, we're going to go ahead and apply a test to that and see what happens. So here's the test. I apply a 0 dBm blocker and measure the noise figure at 20 megahertz offset, and unfortunately the noise figure goes up to 14 dB. And this is simply because when this 0 dBm blocker comes in, it saturates the stages in the LNA, and of course that raises the noise figure. So with a few modifications, we can actually get there. We apply that concept around the first stage as well, and another bank up there without going through the details. And what we see is that now, with a 0 dBm blocker, the noise figure goes up to 2.1 dB, so it's a pretty reasonable amount. And with these, what we can see is that we have checkmarked almost everything on this list as in terms of what I call the universal receiver. Now, this is actually not quite correct. When I said wide frequency range, yes, I can adjust the LO frequency and receive any signal from lower frequencies all the way to some gigahertz range. But we have to remember that these switches are driven by the local oscillators, and that switching action creates mixing with the harmonics of the local oscillator as well. And because we don't have any other filtering up front, any blockers at the harmonics will also come into the circuit and will not be rejected by what I showed you. So here's the situation. We have the desired signal at some frequency, the blocker at 3F1, we have some sort of mixing, etc. And the LO has its harmonics, or the mixing action creates harmonics. So we will end up superimposing the down-converted blocker at 3F1 over the down-converted signal at F1. And that causes problems. So of course, as you know, there have been many approaches to this issue. One is harmonic reject mixing, but we can also perform harmonic filtration. So I'd like to talk about the second a little more to show you what people have been doing. So here's an interesting example from Fabiano in ISCC 13, where he says, I have a down conversion mixer, and in the baseband, I will place a tank resonating at the center frequency of 4 FLO. So LC resonates at 4 times the LO frequency. Now, we know that this network will be upconverted by this mixing action as far as Z in is concerned. So this upconversion mixes 4 FLO with FLO, giving something at 3 FLO and 5 FLO. So Z in has a high value at 3 FLO and 5 FLO, which means the signal coming in, if it's coming from a high impedance, prefers not to flow to the baseband if it's located at 3 FLO and 5 FLO, meaning the harmonics of the LO. So because it doesn't flow, it doesn't get down converted, and as a result, equivalently, we have a notch at 3 FLO and 5 FLO. So that's a cute and interesting idea. The only thing is that if you are looking for a broadband system, this will not suffice, because if LO is allowed to vary by a factor of 100 or something, this center frequency has to track it, and that would be complicated. Well, another way of thinking about this is to go back to our commutated networks. This time I just showed you one capacitor connected by 4 switches to a current source. You can see that this current source connects to the top plate of C1 when the top and bottom switches are on, and it connects to the bottom plate of C1 when the 2 cross-coupled switches are on. So it's almost like a full wave rectifier. So if we examine what's happening here in the case of an input sinusoidal current at exactly the LO frequency, we see that a positive cycle, it goes to the top plate of C1 because the top and bottom switches are on, and a negative cycle also goes to the bottom of the capacitor because then these 2 cross-connected switches are on. So for this particular case of a sinusoidal input at the LO frequency, we see that the voltage on this capacitor keeps accumulating indefinitely. So we have a full wave rectifier injecting the sinusoidal current onto the capacitor. So that means that when I examine VAB, which keeps scanning the voltage across C1, I see a voltage whose amplitude is growing indefinitely. So in response to an input current with a finite swing, we have created a voltage with infinite swing at the LO frequency. That means that the input impedance at that frequency is infinite, which is the same as upconversion of the capacitor impedance to the LO frequency. Now, this type of perspective allows us to also look at the third harmonic and see what happens. So at the third harmonic, we apply a sinusoidal current at the third harmonic of the LO, and again monitor the accumulation across C1. And we see that again we have accumulation because we have, for every LO half cycle, we have a net charge because these two cancel each other, but we still have some positive charge deposited on the capacitor. So the voltage on the capacitor still accumulates indefinitely, maybe more slowly, but it still does, which means the impedance seen between A and B at the third harmonic of the LO is also infinite. But this gives us a simple rule of thumb. If we want that impedance not to be infinite, meaning if we want to reject the third harmonic, we have to make sure that the capacitor does not accumulate anything but zero charge in one LO cycle. So based on that, we can go ahead and build something else. So this is the rule of thumb we're going to use. The capacitor must not accumulate charge indefinitely, which means the net charge delivered to the capacitor must be zero in one LO period. All right, well, let's take three capacitors driven by 0, 120, and 240-degree phases and drive them with a current source. In this case, what we see is that because we have these three cycles and we look at the accumulation, we see the accumulation is zero, and hence we reject the third harmonic. So if we have a blocker coming in at the third harmonic, because these capacitors do not accumulate charge in one LO cycle at the third harmonic, they will reject it. So we're going to take these capacitors and place them around an amplifier in the style I showed you before. And now we see that at the fundamental, we have the bandpass response we expected at, let's say, 2 gigahertz. This is the LO frequency. And then at the third harmonic of the LO, we have some rejection. So compared to the first harmonic, we have about 48 dB, 40-some dB of rejection. So that agrees with our intuition that we should be able to remove the third harmonic by this simple trick. Now, sitting there, you might be wondering, how do we generate these phases, 0, 120, 240, because typically we have quadrature phases. So there are some tricks we can play. One is we can, as shown in this paper, we can take an LC oscillator and injection lock a ring oscillator to it to generate those phases. Or if the frequency is high enough, we can just interpolate between I and Q to generate the 120 and 240-degree phases that we need. Okay, so let's switch gears to the transmitter and see what we need to do there. So again, all of those issues I mentioned before apply here as well. And in particular, we are interested in linearity and out-of-band emission and high TX output power. The power amplifier is the bottleneck here, and the question is, how do we handle that? As you know, there are numerous techniques for transmitter linearization. One popular method is polar modulation, where we take the signal and separate it into envelope and phase, and then process them independently and eventually combine them inside the power amplifier. This circuit is very mature, but it still has a couple of important issues that become particularly important as we go to higher data rates in these systems. The first issue is the delay mismatch between the envelope path and the phase path. And we can quickly quantify that if we write the signal at the output as some delay associated with the envelope path and then the phase. And we can expand this in terms of its first two terms of the Taylor series to find a desired component, the first component, and an undesired component, which is proportional to the derivative of the envelope and the mismatch. So for example, if we assume that the envelope has a flat spectrum with a bandwidth, with some bandwidth, And then we find the spectrum of this unwanted component. It comes out to be like this. We can integrate that and find the signal-to-noise ratio. The signal-to-noise ratio at the output of the transmitter will be given by the simple equation. And for example, if we assume the envelope has a bandwidth of only 1 megahertz, which is probably not sufficient anyway, and we want to have an SNR of, let's say, 30 dB, so that the signal coming out of here for 64 QAM is not already heavily corrupted, then this delta T is about 300 picoseconds. And it's really difficult to guarantee that these two paths match within 300 picoseconds with all the circuitry that is involved. The second issue has to do with the nonlinear capacitance at the output of the PA, the junction of M1, for example. And the issue here is that as the envelope signal propagates through L1 and comes to the output, it modulates this capacitance and hence modulates the delay in the phase path. So that creates some phase distortion and hence out-of-channel emission. So we can quantify that as shown here, and we can see that again it's a problem in terms of how fast the envelope changes, how large the envelope is, and what type of Q we have in the output network. So we can still continue to work on polar modulation, but we can also explore other techniques. And one interesting technique is complex pre-distortion. Now, you might remember from your circuits and systems theory that for a linear dynamic system, we can write the output as the convolution of the input with the impulse response. But there's another way of expressing the output, and that's in terms of the input itself, a delayed version of it by T1, another delayed version of it by T2, et cetera. For example, T2 can be 2T1 and so on, with some real coefficients, alpha 0, alpha 1, et cetera. So that's a nice way of writing the output for a linear dynamic system. Now, if the system is nonlinear and dynamic, maybe we can extend this and say that the output now consists of these linear terms plus some higher powers. So we still have those, and then we have x squared terms that are delayed, and then x cubed terms that are delayed, et cetera. This is somewhat 2 Volterra series, not quite. But our guess is that for a well-behaved system, we can write something like this. So now, if we have that, and we have a nonlinear PA, what we are hoping is that we can place some block before the PA, some pre-distortion block before the PA, that will cancel the dynamic nonlinearity of the PA. So we just want to put some block in there. Now, given that the response of the PA can be expressed like this, the response of this inverse function can also be expressed like that, approximated by that. So we're going to put something in there, a bunch of delays, a bunch of polynomials, and then some combining action. This was done by Roger in ISCS 13. He has implemented this in the analog domain, so it's a little complicated, but the hope is that eventually we can implement this in the digital domain. Now, pre-distortion always makes one assumption. The assumption is that the PA is not infinitely nonlinear. In other words, if the characteristic of the PA is completely nonlinear, then no amount of pre-distortion can correct it, because these terms would have to go to very, very high orders. So that is a problem. Eventually, we would like to have a PA that is arbitrarily nonlinear, but with this technique, it seems that we can't do that. Well, we can. And the reason we can is that we can envision a situation where the input to the PA is not analog. If the input to the PA is not analog, then that nonlinearity won't bother us. Well, it will bother us. We have to correct for it, but even if it's abrupt, we can still correct for it. And by that, I mean we can drive the PA by a DAC, or we can replace the PA by a DAC. So if you go back to the concept of software radio and revisit this notion of driving the antenna by a DAC directly, then any pre-distortion can be done in the digital domain and apply to the DAC and take care of all of the DAC output nonlinearities. So there have been some examples in that domain. The DAC is a tough design. In fact, 5 years ago, we might have thought that it would be impossible to do something like this. It requires a high linearity, high resolution, low out-of-band emission, fast linear settling, and a high output current. But interestingly, there has been quite a bit of progress in this domain. Here's an example from MediaTek where they use two INQ DACs to drive the antenna directly, each of them with a resolution of 13 bits. And they use a lookup table to correct some of the imperfections of the DACs. It doesn't take care of dynamic nonlinearities, but at least it takes care of static nonlinearities. I don't remember if it's only at the startup or in the background, but it has some correction for that. So these are initial steps that we have taken, but they are quite promising. You can see that we have removed most analog functions that you would see in a transmitter in terms of AGC and DC offset cancellation and all that stuff. For 11G signals, they have reported an output power of 18.8 dBm with 17% efficiency, which is a pretty good number compared to fully analog solutions. A few words about phase noise before we wrap up. The phase noise is also critical. Here's an example of phase noise removal at a higher level than oscillator level and synthesizer level. In this case, they recognize in the receiver that when we down convert and we mix the phase noise of the LO with a large blocker, we have these skirts sitting at some frequency away from the desired channel in a direct conversion receiver. Then they say, well, why don't we try to reconstruct this profile without the desired signal and try to subtract it. To reconstruct that, we're going to pass it through a high-pass filter, limit it so that we remove the AM, and then we pass it through a low-pass filter, and that gives us the one side of the skirt. Now, if we subtract this one side from this combination, we will remove the corruption that this phase noise has created in the desired channel. So that's an interesting idea, but it does not reduce the effect of phase noise on the signal constellation itself. In other words, in the absence of a blocker, the phase noise still rotates the constellation. And also, this idea cannot be applied to transmitters. It's only for receivers. Well, another approach is to go back to our good old charge pump phase lock loop, type 2 PLL. And we know that the bandwidth of this loop is typically on the order of the reference frequency divided by 10 or 20 for stability reasons and for spur reasons. And we say, well, why can't we just replace this with the type 1 PLL, which we are familiar with from olden days? Because we know that this filter, this system can go up to at least FRF over 2 in terms of bandwidth, because it has only one integrator in it. But the problem is that the output of this XOR swings from 0 to VDD and creates a very large amount of spur at the output of the VCO. So why don't we replace that filter with a switch capacitor network so as to mask the transients at the output of the XOR? This still doesn't work because for half of the cycle, we present the XOR output to the VCO. Then maybe we can replace that with a master-slave sampling filter so that we create a solid voltage at the control of the VCO. So now the VCO control is relatively clean, and we can achieve a bandwidth on the order of FRF over 2. This allows us to remove the phase noise of the VCO all the way to FRF over 2. And now it turns out that we still have some ripple on the control of the VCO, which we will take care of by these harmonic traps. And the result is that we can achieve a frequency synthesizer that is good enough for example, 11ABG at 2.4 gigahertz with only a simple ring oscillator rather than an LC oscillator and a moderate power consumption. All right, in closing, I would like to make one more prediction, which is crazy but interesting. Today, you can buy a toy, a little helicopter that can be controlled by your brain waves. There's a simple wireless connection from here to here, and you can fly it up and down. So we are actually reading our mind, so to speak, and we're not that far from it. In a program in Germany, I think, in brain flight, they have been able to control airplanes using brain waves, well, at least in simulators, not in reality. So that brings up a point that maybe in the future, wireless technology can be used to remove the keyboard interface altogether. We don't need to communicate interface with our devices through a keyboard or touchpad. We can just do it by our brains. And so sometime in the future, maybe by 2020, you will be, instead of texting, you will be minding to your colleagues. I thank you for your attention.